Hello and welcome back to Dynamic System Modeling. In today's session, we will continue our discussion about transfer functions. Namely, we will be focusing on the analysis, in particular in zeros and poles. So what are the zeros and poles of a transfer function? Take the example that you have a transfer function equal s plus 8 over s minus 2 s plus 6. So the roots of the numerator are called the zeros of the system for the transfer function. And the roots of the denominator are called the poles of the transfer function. Why this is so? Why it is called zeros? So if we solve this, if we find the roots of the equation, of this equation, s plus 8 is equal to 0, then s equal to minus 8. This is a 0. Why? Because if you substitute minus 8 there, so minus 8 plus 8, this turns out to be 0. That's why it's called a 0. Now let's find the poles of the transfer function. S minus 2, s plus 6 is equal to 0. S equal to plus 2 and s equal to minus 6. So if let's assume we substitute s by 2, so 2 minus 2, it will turns out to be 0. Any number over 0 will turns out to be infinity. So it takes the system to the pole of a certain behavior. Now remember that S has been defined previously as a complex frequency, okay, and it is in the following form: real part plus imaginary part. Thus we could plot those zeros and poles on a complex plane in which we have the real part. This is the imaginary of S and this is the real part of S. And we will denote the zeros by circle, okay, and the poles by a cross. So S is equal to minus 8 is a 0, so we go and plot it, minus 8, blah blah blah, minus 8, okay, and we draw a circle at minus 8, indicating that there is a 0 at minus 8. S is equal to 2, we put a cross, and this is a 0, and this is a pole, and S equal to minus 6, okay, this is another pole. What if we have a function, okay, transfer function h of s is equal to, again, s plus 8 maybe, over s squared plus, assume you have 2s plus 5. Now if you find the roots of the denominator, the delta is equal to b squared minus 4ac, this is 4 minus 4, 1 by 5, it turns out to be minus 16. So we know that there is no solution for us. Alternatively, we could change them as they are in complex domain. We could change this into plus 16i or j squared, okay, and then we can solve this equation. S12 double solution is equal to minus b, which is 2 plus minus radical delta, which is 16j squared over 2a. So we end up with minus 1 plus minus radical less 16 is 4 over 2 is 2, j squared is j. So those are called the poles of the system. And s equal to minus 8 is the 0. Okay, now let's plot the zeros and poles. Okay, we have s equal minus 8. We have a 0. Again, remember this is the imaginary part, this is the real part. And so this is minus 8, it is a 0. We have s equal to minus 1, this is the real part, plus 2j, this is 2, okay, and we have a cross. Okay, this is a pole. and minus 2. Okay, at 1, minus 1, another pole. So we have 2 poles and we have 1, 0. Remember in this case, if we look over the Laplace table, or we perform the inverse Laplace, this will give some oscillations. Remember this. Now, if we want to analyze them, I'd like to say something very important, that the poles to the negative side of this plane, of this complex plane, indicate that the system is stable. And if they are on the imaginary axis, the system is said to be marginally stable. And if they are to the right side of the complex plane, okay, the system then is unstable. Clear? Let me take a simple example. Okay, if I have like 1 over s plus 2. Okay, so there is no zeros for the system. There is only one pole, which is equal to s equal minus 2. If I want to plot it, okay, s minus 2, okay, it is on this location. This is a pole. Alright, now let's convert this back to the time domain. Of course, I'm not considering the input, or assume the input is an impulse function. So 1 over s plus 2, the inverse of it is e power minus 2t. So if we plot the pole, it is a function, okay, without any oscillation, and it converges to 0. So as t tends to infinity, okay, this turns out to be 0, approximately. So this is the plot of it, right? So of a power minus 2. So the pole at the left side of the plane tells that the system is stable. The system diverges to a certain value, okay, as in this case. Take another example, that s is equal s minus 2, okay, then the pole is equal to s plus 2, right? So if we want to plot it, plus 2, okay, this is the pole. Now let's think from the time domain perspective. If we convert this to a time domain, we have e power plus 2t, and we want to plot it, okay. So as the t tends to infinity, this component, the exponential, tends to infinity. So it goes like this, and it diverges. That's why we said this is unstable. Now, in case we have complex component, we know that this will be converted into cosine and sine. If you look back over the previous sessions, you know that the inverse Laplace of this will yield some component in which we have e power, maybe some component at cosine omega t plus something, right? So we have some oscillations. So this component will be like this. Okay, so there is oscillations, but at the end they maybe vanish. Okay, so they are stable, but in order to achieve this stability, the final steady state response, then the system has some oscillations. If we have a complex pole to the right of the complex plane, like in this scenario, right, then there will be some oscillations, okay, but those oscillations start to increase and increase until they diverge into something which we don't know how the system will behave, okay. So in summary, we have the imaginary part, we have the real part. If the pole is found to be on the left side of the complex plane, is said to be stable, okay. If it is on the x-axis, then there is no oscillation. If it has some imaginary part, there will be some oscillations, okay. In the right side of the complex plane, it is unstable, okay, unstable region because it diverges, okay. And of course, if we have some imaginary part, there will be oscillations, and also divergence. And again, if we have a pole on the complex, on the y-axis, which is the imaginary, okay, axis, okay, and then it is called marginally stable. Marginally stable. Okay, so let's assume we have a solution, okay, like a pole in this location. Then the plot of this will be looks like this. Okay, and this is in ideal scenarios. Okay, the oscillations will not vanish. Okay, like a sine wave, cosine wave. Okay, so that's why it's called marginally stable or a critically stable system. Okay, thank you. That's all. All right, see you.